I forget something or the other every day. Anyway, so as I was saying, Coq is this proof assistant, right? At its core, it has a nice functional programming language. It's simpler because it doesn't have mutability, so no references, no arrays, and so on. But it is much more powerful in the type checking sense. So as we will see, we can do very rich things with types. And actually, our way of proving things will also be just using types. So today, what we will do is we will start with some basics of Coq, and then I will sort of hint towards proving things in Coq. And what does it mean to write a proof? What does it mean to write a theorem? And what do you get as a result of writing a proof? Right. So I mentioned before in the last class that proof assistants help you construct the proofs, but mathematically check it. We'll see all of that in this class, right? So you'll at the end of this particular lecture, you will get an idea of what it means to express a small program and then prove properties about it using a proof assistant, right? And we will only scratch the surface. We'll see a bunch of things today, but as we go along in the rest of the classes, at least in the first half, we will see more and more stuff with Coq, right? So, and then we will switch to F star um, maybe we'll come back to Coq as well, based on how far we get. Okay, so this is stuff that is not from the FRAP book. The formal reasoning about programs book is starts at a little bit of advanced level. We will also cover that. But what I wanted to do, I found personally this introduction to be useful, as it nicely jumps off of the OCaml parts of the 3100 course. Okay, so this is Coq IDE, and you should install this IDE. And if you haven't installed, go install it. There are binaries available. If you just search for Coq IDE, you'll get this IDE. I think my version is 8.13, Coq IDE version 8.13. I recommend everyone to use the same version. I have added instructions in the course website under resources. If you have any trouble at all installing this, just let me know, and then we can have you set up. I believe this works under Windows, but I haven't tested. So again, I don't know anything about Windows. I know it for sure. It works under Linux and OS X. Okay, so Coq has support for basic type definitions and writing functions over it, right? And here is a type definition. And this is just like OCaml's algebraic types, right? And the syntax we use here is should remind you of the syntax for GIDTs, right? Where we said there are a bunch of constructors, right? And then each of the constructor gives you a value in this data type. So let's read it from top to bottom. So in OCaml, we will write type here. We write inductive here. These are minor differences. And the type's name is day, right? So we are defining a type called day. And this thing itself is a type. So Coq has a very advanced type system, right? Um, so one of the things that we can do is types itself have other types in Coq. I mean, this might be mind bending at the beginning, but as you go along, you will see that this is one of the most powerful concepts that you can have. But this is not important here. You can skip this if you don't want to write it here. But what we claim here is that I'm going to define an algebraic data type called day. And there are going to be 7 constructors. Each of these constructors are starting with lowercase letters. So in OCaml, you have to name the constructors with uppercase. That's not necessary here. They are lower cases, right? And each constructor is nullary. It doesn't take any arguments. It just says Sunday is a day, Monday is a day, Tuesday is a day, and so on until Saturday. And there are a few other differences. We use colon equals here instead of just equality in OCaml, and we have a dot at the end in order to terminate the definition. So these are syntactic differences. You'll get used to it as you go along. And all we've done here is essentially saying, oh, there is a type called day and it has 7 constructors. I mean, this is no different than what you might do in C with enums, right? I might just define a enum called day with 7 different values, and that's precisely what I'm doing here. Okay, so that's done. Coq has this interactive way of going ahead and checking your program so far, type checking your program until this point. And what we are going to do here is there is this navigation pane, right? So there is forward one command, backward one command, and go to cursor. So these have shortcuts as well. So essentially, the navigation thing has a bunch of shortcuts, right? What I'm going to do is to press command right arrow on Mac OS, and what it does is it highlights everything in green. And the way you should read it is Coq has type checked up to that point, and it thinks that everything is okay so far. Okay, so this is the way of interactively building programs and proofs, right? So this is very similar to what the workflow you would have in Jupyter notebooks, right? You write something and then we sort of run it, and in OCaml it says okay, everything is fine. It's similar. So the workflow of Coq when developing programs is actually we rarely do batch compilation. We don't ever say, okay, here is a file, go compile it. When we are actually developing it, we sort of incrementally compile. The key combinations might be different on your machine, but what I'm doing is this go to cursor. So I place the cursor somewhere and I press right arrow, it type checks up to that. Okay, so that's the type definition, right? So once we've defined the type, we can go ahead and define functions based on the type. So here is a function definition. So in OCaml, we will use a small lowercase let here. We use a uppercase let. Next day is the function name. It takes a day, and then we pattern match on day, right? If the day is Sunday, then the result is Monday. If the day is Monday, result is Tuesday, up to all the way through, right? We cover all the cases. And this is just plain old pattern matching that you would find in OCaml. So we have exhaustivity checks as well. So if you remove a particular thing, so you will get a error message here saying non-exhaustive pattern matching. I forgot to mention what these windows are. So this is the actual program that you're writing. And you will see something appear later here. This is essentially Coq will tell you when you write a proof, when you're proving a theorem, it will tell you what the sub-goals you need to prove here. Okay, so that will appear here. And these are essentially the error messages and so on. So you will see these three windows all the time when you work with Coq. And what we're doing here is we are just defining this function. Ignore this warnings. This just has to do with the language evolving, and these definitions sort of using the old syntax, but that's fine. Okay, so let is one way of doing it, but the idiomatic way of doing the definition in function definition in Coq is actually using this thing called definition. The difference is a bit technical. So let gets substituted away. Sometimes you really want to appeal to definitions in your proof. So I think this is the last time you'll see let at the top level. We will always use definitions from now on. And essentially we are defining another function. You can substitute let for definitions, but always stick to definitions. And here is a function that defines previous day. And this does whatever you would expect, right? So Sunday, previous day of Sunday is Saturday, and so on. So observe that there is also a terminating bullet point at the end, right? So that's worked as well. Any questions so far on this? Any observations, questions? No? Okay. In which case, let's actually go ahead and write a first theorem. Okay. So here's the way you would define a theorem. So we say, I mean, the theorem is very, very simple, right? All I'm claiming is Wednesday comes after Tuesday, right? So that's the name of the theorem. And then I write a colon, and then I say, I write an expression here, right? This is just an expression which says next day of Tuesday equals Wednesday, right? So this should look very intuitive now. So next day is the function that we defined earlier, right? And again, Tuesday is one of the constructors and Wednesday is one of the constructors. So this should look obvious, right? So the how the thing that you should realize is we cannot do this in OCaml statically, right? We cannot say that evaluating this function with the argument Tuesday will give you Wednesday at compile time in OCaml, right? You can add an assertion which says that assert next day of Tuesday is Wednesday, but that is like a runtime checking, right? But what we are going to do is actually write this thing down and prove that next day of Tuesday is Wednesday. So we prefix this thing with theorem, and the name of the theorem is Wednesday after Tuesday. So if you write it down and you sort of say, compile it up to here. So Coq gives us one sub goal, right? Coq says that you have to prove that the next day of Tuesday is Wednesday, right? And now it sort of throws the ball in our court and says, go ahead and show me that this is in fact the case, right? And there is one sub goal, and this is one of one. That's the first sub goal. And you can read this as how we've written the static semantics, right? There are no assumptions here, and you have to show this particular thing holds, right? And how do we show this? I mean, the obvious thing to do is to say, go and actually call next day, right? With the argument Tuesday, you will get Wednesday, and the Wednesday equals Wednesday, so that's why it is true, right? So this is what we need to communicate to Coq, and Coq will get convinced at that point. And the way we sort of inform Coq about what we need to do, these steps, right? And these are precisely what are known as tactics. And what tactics are a way to manipulate the proof state. So what we have here is known as the proof state, and tactics are these commands that we communicate to the underlying Coq system to say, this is how you go ahead and prove this thing, right? So the way you write proof is you start with this keyword called proof. And then our first tactic that we are going to see is a tactic called auto. Auto just says there is some magic going on. Automatically try to prove this. And Coq will go ahead and say, I know certain things that I can do. In particular, if I see a application of a function to a concrete argument, I can go ahead and reduce it, right? And it knows other things as well. So it is going to try a few of those. If it is able to succeed, it just comes back with the proof. So I said auto. Coq was able to do something and able to prove it. In particular, it basically reduced it and said, okay, this is going to be the same argument. So that's why it succeeds. And there are no more sub goals. We are done. So now you say QED, and we've done our first Coq proof, right? So we proved a theorem. And actually, one thing that is very interesting with the way Coq works is that it doesn't use classical logic; it uses constructive logic. It's okay if we don't need to dig into the difference, but an implication of using constructive logic is that whenever you build a proof, you actually have a proof object in your hand, right? So this thing is actually a value in the program, right? The proof of theorem is a value, and we can print what Wednesday after Tuesday is, right? And the way to sort of interpret this is, I am looking at the actual proof of Wednesday after Tuesday, right? And Coq says Wednesday after Tuesday is this thing called EQ-REFL, right? And that's the proof for the theorem. The theorem, this one. So what is the theorem? It just says next day is of Tuesday is Wednesday, right? And what is EQ-REFL? EQ-REFL is from the Coq standard library, right? Now you should just read it as Coq just knows that equality is reflexive, right? If I give some term on the left hand side on which I can apply equality, and the same term on the right hand side, right? And my proposition that I want to prove is, say, A equals A. EQ-REFL allows you to say, okay, that is true, right? So that is all eqrefl says, and that's the proof, right? And why is that the proof? We know that eqrefl internally also does all of the reductions, simplifications possible. So eqrefl just says go ahead and reduce all the terms as much as you can, and then at some point LHS is going to be equal to RHS. I know if LHS is equal to RHS, then eqrefl makes the proof go through. And that is how the proof works. Okay, so that's the first proof that we've done. Questions on this so far?
Casey, one quick question. So on line 41, right, when you issue the print statement there,
Yeah.
I know you mentioned that on the right hand window you can see the equality reflexive, and then I know how that works. But in general, right, under the hood, when you issue that statement, does it actually invoke the match and the method itself, or does it look at the theorem and then decide to output by this thing? How does that work?
Good question. So when you actually print it, so the thing that you're defining here is like a type. Every theorem is just a type, right? So this goes back to the Curry-Howard correspondence that we had seen in the OCaml lectures. Essentially, what we say here is just a type, right? So it's sort of hinting the fact that we write the body of the what we are proving in a theorem on the right hand side of this colon, right? And what we are actually printing is just the value. And we are not actually going ahead and reducing at that point. The value has been constructed using the proof that you've done. So when you interact with the Coq using these tactics, what you're doing is actually constructing a value. And this value happens to be the proof of this theorem. And printing just prints that value. So it is not going ahead and evaluating at the moment you actually print, because you prove this theorem, the value is just printed. Does it sort of answer your question, Sachin?
It does. But then I had a follow-up question based on what you mentioned. So you mentioned that Wednesday after Tuesday is ultimately a type, right? A type whose value is kind of predicated based on the theorem that we proved.
Yeah.
Now, let's say for some reason I decided to kind of make a mistake in my theorem, right? I said next day Tuesday equal to Monday, for example, and then obviously the proof fails. It cannot be proved.
Yeah.
Right?
Let's try this, right? So yeah, this
So
does not go through. Yeah.
So it won't even fall through to the print, right? It will fail.
Yeah. You can't proceed.
Okay, gotcha. Okay, that answers my question. Thank you.
Okay, wonderful questions. Kirti is coming. Okay, so we will see much more regarding this this Curry-Howard correspondence, right? So in the next lecture, I think in the next lecture or the lecture after that, these things are really beautiful. So they are constructed with exactly the things that we've seen in lambda calculus. So all of these might seem like, oh, there is a lot of new infrastructure that is being built around all of this. Yes, there is, but the underlying principles are so simple. They are just direct applications of Curry-Howard correspondence. So if you consider type as a theorem, then the value that corresponds to that type is the proof. And that is what we are going to do all the time, right? This is true with both Coq and F star. This is one of the coolest ideas that I've recently, and not recently, I've come across. And really going through this course solidifies that idea a lot. And you will see that very quickly. We won't appeal to it all the time, but that is what is happening underneath. Okay, so that's the first theorem and proof. So here is, so we used auto, right? Auto does some magic, but really most of the time you can try auto, but auto will might work for simple cases, but not work for more complicated ones, right? So it is better to actually intuitively think before you actually go ahead and prove with the proof assistant. So again, at the end of the one thing that you should consider in your mind is that Coq is going to help you write proofs, right? And it will do all the bookkeeping, but the thinking has to be done by you. So blindly going ahead and applying tactics will never make it work. So it is better to understand how something is proved. And for this particular case, it is very simple. So we are saying, okay, there is next day is Tuesday. I know that the next day is a function. If I just apply simplification, if I just do reduction on this term, I will get Wednesday, right? And they are trivially equal at that point. And we are going to use those as two new tactics. So we saw one tactic auto here. We are going to see two new tactics. One is simple and another is trivial. So what simple does is it simplifies any terms in the goal, right? So that can be simplified by just looking at the definition. So when you apply simple, observe that the proof state is changing, right? So I have next day is Tuesday here. When I apply simple, the next day Tuesday becomes Wednesday. Now I just need to show that Wednesday is Wednesday. There is a tactic called trivial, and all it does is it makes trivial things go through. In particular, it makes equality. It knows that equality is reflexive, and it makes it go through. So if you do that, then the proof goes through, right? So observe that there can be many different ways of constructing a proof for a theorem, right? And in this case, it happens to be the case that if I print the proof for this new theorem, Wednesday after Tuesday prime, it happens to be the same one. It is eqrefl as well, right? So oftentimes there might be multiple ways to get to a theorem, but only a limited number of ways in which the theorem actually holds. So tactics are this very imperative way of interacting with the state, right? You have a state, you modify it, then it goes on to do something else and so on. But at the end of the day, we are constructing a proof using tactics. And that's the idea that you should take away. So let's do more theorems. So here is, make it a little bit. So here is, oops. Okay. Okay. So here is a theorem which says that a day never repeats, right? So if you have a day, then the next day is not the same day. And for this, we are saying for every day, the next day is not the same day. So the way to read this is for all days where D is a day, next day of D is not equal to, so this is not equal to in Coq, D, right? We intuitively believe that this is true. I mean, how would you go about doing this proof if you were to do this on paper, right? I know there are 7 days. I know that the next day of each day is so and so, and if you look at each one, then you can see that the day doesn't repeat, and that is exactly the proof that we are going to construct for this particular theorem. So Cox says that oh, now you have to show me under no assumptions that for all D days, the next day of D is not equal to D, right? You can try auto, right? I'm starting a proof. I try auto. Auto does nothing here. Auto says, okay, I tried some things in my repertoire, but nothing has worked out. How can I actually go ahead and prove this? Go back to our intuitive definition, right? So we have to iterate through each of the days, and then we want to show that for each of the days, the next day is not the same day. And that is precisely what we are going to do. We are going to see a few more tactics. First one is introduction, right? So intros, what it does is it sort of says, okay, there are many days here. It says for all days, right? So if you apply intros D, all it means is that I'm not assuming anything about the day, right? I just pick D as an arbitrary day, right? So, and I push it to the assumption. I know D is a day, but I know nothing more about it. I'm going to, the way to read this is for an arbitrary day, I want to show that next day of D is not equal to D. And that's the difference between before and after. I mean, technically, this is, this is the same as for all, but we are pushing it to the assumptions just so that we can manipulate it further, right? I pick an arbitrary day, and then I want to say, now look at all of the days, all of the values that this day can take, right? So that's the next step that I want to say. And for that, there is a new tactic called destruct, right? And destruct D says there are several options for D. Pick all the options that you could have for D, right? And if you do destruct, observe that there was one goal, now it has become 7 goals, right? one for each of the days. And how would you go ahead and proving this? So we can try to do the same way as earlier. We can simplify it. If you simplify it, we get Monday not equal to Sunday. So in Coq, trivial does not make inequality go through. So hence we have to use this tactic called discriminate. I am operating at the very low level. We will study more and more advanced tactics where all of this will go through. But for now, it is better to understand the low level tactic as well. So we want to show that Monday is not equal to Sunday. Essentially, Monday is a value and Sunday is a value. They come from the same constructor, but we want to say these two are different. And in order to say that these two are different, we use the tactic called discriminate, right? And that makes that particular goal go through. And we have 6 more goals. And for all of those, we just repeat the same thing. So there are no more sub goals. We are done, right? So the new tactics were intros, which introduces, which basically takes the for all value and then push it up to the assumptions. And then we had destruct, which just said, okay, you have some arbitrary day, pick all the values. Essentially, destruct is doing case analysis, right? So if you look at this position, I have a D day, and there are 7 cases for D. So destruct essentially says pick case 1, case 2, case 3, case 4, case 5, case 6, case 7, and then you are going to do something to manipulate it. And destruct is essentially breaking it apart so that you can do case analysis, right? So that's what destruct is doing. Any questions on this so far? How this went through? Would auto have worked after destruct? Let's try that one. I really don't know. Let's try. No, auto doesn't work. So let's try after simple, right? So there is simple. Does auto work here? Auto doesn't do. Yeah, one thing that you'll find surprising and a bit frustrating is that these auto rules are sort of magic, right? And they are. It is not. It won't be clear what all they try. They have some heuristics, right, and which they try, but it wouldn't be immediately obvious. We'll see if this works. Yeah, so there is a thing called debug. I am sort of moving ahead. It's okay if you don't understand this right away, but this debug applies to auto, not for all of the rules, but debug applies to auto. And what it's doing is it's printing a log of all the things that auto tried. Okay, so the way to read this one is that it's a tactic that auto tried, and auto said, "Can I just is the goal that I'm trying to prove, right? Is it just part of the assumption? Is there an assumption which just assumes the same goal? If so, then it works. If it doesn't, so it fails." And then it tried intro, and then it tried a bunch of things, right? So don't worry about all of this. All of these are just tactics. So auto has tried all of these tactics, and then it failed. So it said, "Okay, I'm going to stop." And that's what happened. Does that answer your question? Vishnu is the one who asked. Yeah, okay. So you can try debug auto. Okay, so Sriram?
What if the reduction doesn't terminate?
Really good question, Sriram. So we are going to assume that everything terminates. So Coq will be very, very adamant that you prove that the reduction will terminate. So non-termination is equal to false, right? So every functional program that you write in Coq will have to terminate. And Coq has some very basic, very nice properties actually about how to make things terminate. And if Coq says something compiles, it also has the proof that the thing is terminating. Really good question, Sriram. Okay, so okay, cool. So let's proceed. So there is a lot of tedium here, right? So there is a bunch of repeated tactics here, and this just is not pretty because you are going to do the same thing. So Coq has this idea called and let's come back to that. So let's look at the same theorem, right? And then we are going to prove it using a much shorter proof. And the proof is that we are going to do the same thing first. We are going to intros D, right? And we are going to destruct. And the observation is that for each of the sub goals, I'm going to apply the same set of things, right? I'm going to do simplification and discriminate. So one way of saying go and apply this for all of the sub goals is this tactic called all semicolon, right? And what this says is I'm going to apply this tactic, discriminate whatever follows after all on all of the sub goals, on each of the sub goals. And observe that I have dropped simple here, right? And the reason is that discriminate also does simplification internally. So that's the reason. Actually, I don't need simple here. I added it so that for the sake of completeness. So if you do this, all we are saying is whatever number of goals you have, go and apply this tactic discriminate there. And we know that this will go through, right? Because discriminate is what makes this rest of the proof go through. So that's proof as well. Okay, so that is one way of making the proof short. There is this other way as well. So Coq has this notion of tactics, and then if you sort of think about this dot, right? What is this dot saying? Dot is a sequencing operation, right? So dot says apply this tactic simple, and then apply this tactic discriminate, right? That's one way of reading this dot, right? So if you step back and look at it from a functional standpoint, so dot takes one tactic, and then it takes another tactic that follows it, and then it produces a new tactic that's the combination of both, right? Where it applies the first one and then the second one. So these sort of things are known as tacticals in Coq. So tacticals are like functions that combine independent tactics. So let's look at a tactical that will help us simplify our proof. So here is the same theorem again, right? The day never repeats. And this time what I'm going to do is I'm going to first introduce D, and I'm going to use this tactical called semicolon. And what this semicolon tactical says is that if the tactic on the left hand side produces several sub goals, I am going to apply the tactic that appears on the right hand side. Okay, so if it's going to produce, it's like a map operation, right? So if something is going to produce several things, I'm going to take the thing on the right hand side and apply it to each one. And that is precisely what I'm going to do here, right? That is what we are doing here. So we destructed D, and for each of the cases, we want to discriminate. And all it says is destruct D, you're going to get 7 cases. For each of those cases, apply discriminate. Right? So, and if you do that, the thing goes through. The one thing you cannot do is you cannot see actually the state that is produced right after the semicolon. So I have this intros D. I'm going to destruct and discriminate. If you go to the next step, all the proof will go through. One nice technique for looking at what is happening underneath is you just replace that with the dot. You'll see, oh, there are 7 cases. Oh, that's why I can see that discriminate is succeeding, right? So we will use semicolon a lot in the coming classes, right? So if you want to see what the proof is being constructed, delete the semicolon, add a dot, see what is produced. If you're convinced, go back to what it is, and that will help you debug the proofs. Okay, so that proof goes through. We've solved, we've proved that as well. So now let's do another proof. So we are going to show that Monday precedes Tuesday, right? So the way I've written this proof is for all days D, if the next day of that D is Tuesday, then D is Monday, right? So this is sort of intuitively true. Why is this true? Consider every day one by one, right? It is either the case that the precondition, right, the antecedent of the, okay, so the thing is we are using an implication here. Let me say that first. So the way to read this is P implies Q, right? And I'm saying if the next day of D is Tuesday, then it must be the case that D is a Monday, right? I'm introducing new syntax here. That's implication. And the way you would go ahead and prove this is you would look at each of the days, right? And um, you sort of say reduce this and get the value, right? If it is Sunday, then the next day of Sunday is Monday. Monday equals Tuesday is false. False implies anything, right? So this is from your logic classes in your undergrad. False implies anything. So this holds. This is true, and you keep doing this for each of the days, right? For 6 of the days, this will evaluate to false, right? And for the one day where it evaluates to true, D will be Monday, and D will be Monday is going to be the answer, right? That's the intuitive proof. That's what we will do on paper. So let's do this thing using tactics, right? So once you compile the theorem, you get the thing that you should prove. So for all day, next day, we have this antecedent and we have the consequent, right? So let's now operate on this. So the thing that we are going to do is to say, first pick arbitrary day, then move this antecedent to our assumption. Assume that next day is Tuesday, right? Next day of D is Tuesday. And then we are going to manipulate it, right? So let's see how this works. So intros takes multiple names as well, right? So intros sort of says if you just give one day, it is going to introduce one of them. If you give multiple names, if there are multiple things to be introduced, it introduces all of them. So I'm going to introduce arbitrary day D that corresponds to this one. And I'm also going to introduce next day is Tuesday for this antecedent, this part. Okay. So if you look at this, what has happened is the way to read this is there is some arbitrary day D, right? And I also have the assumption that the next day of D is Tuesday, right? Under these assumptions, I have to show that D is a Monday. That's the way you should read this, right? And as I said before, the way we are going to prove it is we are going to look at each of the days. So we are going to destruct it. So we get 7 possibilities, right? And the thing to observe here is that we have an assumption, right? We have an assumption that the next day of Sunday is Tuesday. This assumption itself is false, right? And for many of the cases, the assumptions will be false, except one case for which Monday is Monday, right? So all others, if you look at the goal, they are asking us to prove, Coq is asking us to prove something that doesn't hold, right? But the idea is that for all of those, each of those cases which we cannot prove, there will be a false assumption. And we will appeal to that false assumption in order to make the proof go through. For the other one, we are going to sort of just use trivial, right? So if I have to explicitly do this, first I will use discriminate. Okay, what discriminate also does is if there is a false in the assumption, discriminate will make that goal true. This is also true with auto, right? If I just use auto here, oh, auto doesn't make it go through. Okay, maybe discriminate only makes it go through. So if I use discriminate, so that particular goal is done. And here, the idea is that in this goal, right, there are other goals. You can just ignore all of this for now. In this goal, we have the assumption that next day of Monday is Tuesday, right? That is true. But all we need to show is that Monday is Monday, right? And this is trivially true, right? We saw this tactic called trivial, which just makes it go through. So I can apply trivial there. So that will go through. And for the others, I'll just use discriminate. Discriminate. Yeah, I can repeat the same thing. Discriminate. 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 So the proof has gone through. Again, so you can see that for 6 of the cases they were discriminate. For one case there is trivial, and Coq has a tactical to combine um, multiple different options that you might want to try. And the thing to observe here is the proof either goes through with discriminate or goes through with trivial, right? So Coq has this tactical called just OR, right? This is just like a short circuiting operator in C or OCaml or something. And all it says is that I am either going to try discriminate or trivial. If the discriminate fails, then I'm going to try trivial. So that's the way you should interpret this. And I am using that in combination with this all tactical that we had seen earlier. So for each of the cases, first try discriminate. If discriminate fails, then try trivial, is what this one is saying. So if you do this, then the proof goes through, right? So all of the cases are solved. You can also do this by discriminate trivial. That also goes through, right? That's a different way of doing this. The way to read this is again like destruct D. You'll have lots of cases. For each of the cases, either use discriminate to make the assumption to appeal to the false assumption, or it is trivially true. Okay. Any questions on this one so far? So one thing you should really do, right? So for this course, you should go through the lectures, these lectures Coq files in your own time by stepping through one by one, right? So that you understand how the proof evolves. I think that is sort of fundamental in how to actually manipulate the proof. So it is not enough if you, I mean, it's okay to sit through the lecture and get the ideas, right? And go back to the videos and get the intuitions. But unless you actually do it yourself, you might find yourself staring at some proof which might be sort of obvious, and you're not able to make it go through because you don't have the right tactic. At that point, it is best to come back and say, okay, Casey, what is this? I'm here. What tactic should I use? I'm happy to answer those sort of questions, right? So don't get stuck looking for the right tactics to prove. If you have an intuitive idea of, okay, I know this is true because I can see that this is true by intuitive proof, but I don't know the tactic, just ping me, right? And or the TAs, and then we can certainly find you the right tactic. One of the things that you would find in working with Coq is we have like a set of tactics that we'll come back to all the time, right? And we are slowly introducing more and more tactics, but at some point, once you actually get trained with using the tactics, you know the right one to use. Otherwise, you might feel stuck, but that's okay, right? So initially, you might feel that you don't know all the tactics, but soon enough, you will remember a few of those. And we are going to appeal to like a few, not a lot of tactics, right? So let me just put it that way. Okay, so that, yeah, Shashin.
Casey, I have a question. So you mentioned just now, right? So I had a question to begin with, and then you kind of made a follow-up point. You said the number of tactics available to us are not very many, right? How many are there? I mean, I'm sure it's finite, but what's the
there are a lot of tactics, Shashin. So let me, I mean, if you just look at search for Coq tactics, you'll get a huge page with tactics. There's probably number in the probably hundreds, right? So 200, 300 tactics. But so the way the course is organized is the initial lectures, you will only use tactics that have been introduced, right? So if we use 4 tactics here, you should be able to do all of this with those 4 tactics. And we might introduce other ones as we go along. And we'll be very, very clear. You will never be in a situation where you have to use a tactic which hasn't been introduced.
Okay. Okay, so the reason I asked that question, right, because you also made a point saying, given that it's an interactive proof assistant, you step through it while learning at least, and then at each step, right, the major learning for you is to figure out which tactic to use next, right?
Yeah.
What would be applicable in that particular scenario.
Yeah.
And also when you went over this particular example, right,
Yeah.
when you did the verbatim version, right, you went
Yeah.
each of the 7 cases, you went step by step, you
Yeah.
went discriminate, and then one of them required trivial, and then you went
Yeah.
on. So my question there is, given that Coq seems to offers a very rich bouquet of tactics,
Mm.
what is stopping us from just writing any theorem, whether it's correct or not, right? So that's the secondary point. What is stopping us from writing any random theorem and then trying to kind of exhaust the tactics available to us to prove it? Does that say anything about the correctness of that theorem itself, or is that just the way
It
it is?
doesn't mean anything that way. So you can start with the theorem that is obviously false, and then no amount of using any tactics will help you prove the theorem, right?
I see.
And that's the thing that you should. Yeah, good question. And that is one of the things that is sort of stumps even experts, right? So if you start with a theorem that is false, then you might just get stuck somewhere, and you will encounter this in this course as well. You will sometimes see you might start with the wrong theorem because the way we do theorems, right? For complex things, we start with some theorem and then we assume certain lemmas. And for some lemma, you might just see Coq might just ask you to prove 0 equals 1, right? That doesn't mean Coq is wrong. That just means that the theorem, the assumptions that you might have put in are incorrect, right? And at that point, you have to sort of ask yourself, are you really convinced that this theorem holds? We'll see all of that this time. So before you start proving things, make sure you have at least a inkling that your theorem is correct. See, the proving a theorem is sort of secondary, right? You have to believe that the theorem is true first, and proof comes later. So I think this is a really good question. I think you'll actually see this in practice. Um, Sriram, you had a question.
Sir, could you repeat what intros does?
So okay, so we are so intros is sort of a bit it does multiple things, right? So if I do first, so I have a for all here, right? And I need to say, okay, in order to prove this, I need to apply case analysis here. So I need to iterate through each of the cases. So when we first do intros D, right? All it says is that because for all says D could be arbitrary, I'm just going to make D an arbitrary day, right? I'm not going to place any constraint. And all for all does is if you have something that can be moved from the goal to the antecedent, it does that, right? And when you see a for all and you apply intros, it picks an arbitrary day without any assumptions and moves it to the antecedent. And similarly here you have P implies Q, right? How would you prove P implies Q? Assume P, then prove Q, right? So, and
So it always first sub goal that we have to prove.
yeah. And it's looking at the goal, right? And it is looking at the goal and it's manipulating the goal term. And of course, it is operating on different kinds of terms differently. So if you have a for all, it just introduces that as a day. And then if you have, say, I'm just using some name intros H, which is hypothesis. It is taking the antecedent and then moving it to the assumption, and then says assuming that this holds, show me that D equals Monday holds, and that is
Got,
I think those are the two things that intros does. I haven't seen. Yeah, so there should be sufficient enough description of what goes on with intros. Okay, so let's move on. We'll have to complete this in the next class, but that's fine. So Coq has a functional programming language at its heart, right? So Coq is essentially this proof assistant, right? But it has languages built into it In particular, it has a functional programming language called Galena, which is the language with which we are writing these type definitions and function definitions, right? And it has this tactic language with which we construct the proof, right? And the tactic language is called LTAC. For whatever reason, I don't particularly know how these names came about, but there are two different languages, right? Galena is a purely functional language that is sort of lets you write functions and types and yeah, essentially functions and types. There is nothing else in Coq. And then there is the tactical language, so which allows you to construct basic tactics and more advanced tactics. So this Galena is purely functional, right? And of course, we've seen lists in OCaml, so you can do list manipulation as well in Galena in Coq. And by default, some parts of the list library is included. There are other parts as well. So this require import is a way of saying, get me all the definitions in this list module, right? And this import is also importing list notations. So the details of this is not important, but essentially we are opening up the list module, and we are also including all of the list syntax as well, right? And we once we included, we have all of the list functions. The lists in Coq are defined exactly the same way we define lists in OCaml. We just use the syntax, GADT syntax, right? So because we already have a type called list defined, I'm going to define my own module. So modules are similar to OCaml modules. They are just namespacing, right? They are a different namespace under which the definitions that appear under the module are combined together. This is just so that my definition doesn't shadow the default definition. So I define a list type, right? Which has two constructors, nil and cons, just like what we have in OCaml. And then nil gives you a list of A, right? List of alpha. And then cons takes alpha, list of alpha. And then what you get back is a list of alpha. So there are a few things that are different here, right? In OCaml, we write as alpha list, right? And then we write beta list. The polymorphic term appears before the actual list keyword. This is more natural, actually. OCaml has got it wrong. Haskell also uses this notation. It's much easier to read this as list of A rather than alpha list. But that's fine. That's just syntax, and we don't talk about syntax. So what we are saying is that there is some A, right? And then nil is just a list of A. So in OCaml has polymorphism. OCaml, you can just say it's a quote alpha list or a quote A list. But in Coq has a very advanced type system, right? So essentially, type inference does not work in this advanced type system. Type inference is beautiful idea, right? So it the fact that it works for languages like Haskell and OCaml is just a wonderful achievement, and we should be happy about it. But as soon as you make it a little bit more advanced, type inference is just an undesirable problem. It just doesn't work. So one thing you will see is that there is some type inference available at limited positions in Coq, but most of the times we just write types explicitly for all of the things that we do in Coq. And the thing that we do here is that we define a list, right? And list is parametric over the content, right? You can have an integer list or a string list or a bool list or whatnot. So we actually take a type as a parameter. So we say list is a type constructor. So it's like a function as well, right? List is a type constructor that takes some type A as an argument, and it itself is a type. So it's a type to type function. For an arbitrary type A, you have a list of A, right? And that is where the A comes from. So no polymorphism. So everything is explicit. But otherwise, the actual construction stays the same, right? There is nil and cons, and that is how you construct a list. And if you look at the Coq standard library, because I've closed this module, this list thing that I'm looking at is the Coq standard library definition of list. So check is this way to check the type of terms, right? Prints the term, check simply prints the types of terms. So I'm checking what the type of the standard library definition of the list term is. So the list term is a type-to-type function. Just like I defined, you can read these type constructors as functions as well. So it's a function from type to type. So again, this is an idea that sort of differs from how we did things in OCaml, right? OCaml has functions that take some values and return some values. Coq is a little bit advanced. It has functions at the type level as well. So list is a function that takes one type and returns another type. And essentially what it returns is that it takes arbitrary type A and it returns a type of lists whose parameters are those types, right? So you will see, I mean, these are just functions at the end of the day. If you just get over the fact that we are having functions at the type level, everything else is the same as what you've understood before. You just apply those same concepts here. So I'll stop here, and then we will continue from this point. Any questions so far? No? Okay. So we'll stop here. I'll see you tomorrow. Thank you. Bye-bye.
Thank you, sir.
Thanks. Bye.
Bye-bye.